Hello and welcome to Lesson 5 in Unit 3 on gravitational and normal forces. Now, in this lesson, we're going to be obviously discussing these gravitational and normal forces. But before we get going on this first example, I want to go a little bit into where the book begins on differentiating between mass and weight. Now, under the heading mass versus weight, it says that mass is the amount of matter in an object. That is exactly correct. So mass is literally the number of representation of how many atoms are in that object. Mass we're going to give in kilograms, and the value of mass never changes regardless of if it's on Earth, or if the object is on the moon, or if it's floating through space. The mass is always going to be static and the same. Weight, on the other hand, weight is actually a value that represents force. Weight is given the formula, we can see at the top of the page under the heading force of gravity. Weight is equal to mass times little g, which represents the acceleration due to gravity. So weight's value is given in newtons, and we're going to use the mass of the object, the unchanging value, and multiply it by the acceleration due to gravity in whatever circumstance it is in. So if it's on Earth, we're going to be multiplying the mass by 9.81 meters per second squared, or on that table, newtons per kilogram, which if you work those units out, it's the same thing. And it's going to give us, well, it's going to give us some sort of weight. There's a small example in the table under mass versus weight. Now, if we were on the moon, and you can see in that same example, where the acceleration due to gravity is only 1.6 meters per second squared, our weight value becomes quite a bit smaller despite our mass not changing. It's the acceleration due to gravity that's changing, which is going to give us a different value. Now, mass and weight in just colloquial English is, they're not really differentiated at all. We use them fairly interchangeably, but in the physics classroom, we're going to try to be fairly specific with our language and keep mass as that unchanging value in kilograms, and weight we're going to use as the name of a force, the name of the force due to gravity. Okay, with that out of the way, let's hop into this first example. Now I have it partly sketched up here already. It says we have a 350 gram mass right here. When we start getting to the force of gravity calculation, we're going to want to make sure we switch this to kilograms, simply because our units for newtons, which is our force unit, are in kilograms times meters per second squared. And so if we have grams, they're not really going to be compatible. Okay, so that's the first thing out of the way. This object is being pulled upward by a force of 8.7 newtons. I've got that sketched on here already. And it also tells us that this object is being pulled upward at a velocity, at a constant velocity, maybe underline, circle that constant value, of 6.0 meters per second, and that is the velocity. Alright. To be honest, the magnitude of 6 meters per second means nothing to me. And I hope that by now it means more or less nothing to you as well. The important key word here is constant velocity. Constant, I'm going to write it out even, velocity. Because what constant velocity means is, well, I hope some of you have got this already, that acceleration of this object is equal to 0. It's moving at a constant rate, but it's not getting faster, it's not slowing down, which means if acceleration is 0, it means that our net force on this object is also equal to 0. Because remember how F net, where do I want to put this? F net is equal to mass times acceleration. Well, if acceleration is 0, This whole thing equals 0. Alright, I think I'll leave these bits up, but I'll get rid of that last little bit. Okay, so Fnet is equal to 0. What else does this question say? What is the force of air resistance? Okay, so the last thing we need to solve. Well, let's finish off our free body diagram, why don't we? Since we know Fnet is 0, we know that sum of our forces on this object is going to be 0, which means we have one force moving upward, and which leaves us with our remaining force, or forces. This is what we're going to have to discern for ourselves. The question is asking us to solve for air resistance. So let's put F air pointing down because it's opposing the motion of the object. Right? But this one we don't know. This is our final answer. Okay. How about the name of this topic? Gravitational forces. Right? This object is being lifted. It's being pulled upward. So basically now, from now on into the future, anytime we have objects being pulled upwards, we're going to be using gravity in the downward direction. So let's sketch gravity on here. And we can say that force of gravity is equal to, we just learned it, mass times the acceleration due to gravity, which we give a little, we call it little g. We're going to be learning about big G eventually, but for now, little g. Alright. These are the three forces in this question. So where do you think we go from here? Well, we could probably discern what this one is and then move on from there. So let's solve force of gravity. Force of gravity is equal to our mass. And remember, switching to kilograms. So 0.35 kilos. And we're going to multiply that by acceleration due to gravity on Earth. 9.81 meters per second squared. And if we plug that in, we end up getting a value of 3.4335 newtons. We also want to put direction on here. I've sketched on my little positive negative direction diagram. Okay, and I'm going to say that this is downward. Because when we get into our net force formula, we're going to want to make sure that this is represented as a negative value. Okay, well with that said, let's just jump right into that net force diagram. We've got the first one out of the way. Force net is 0 because this thing's accelerating at a constant rate. But if we want to find a missing force, we just list off all of our forces. We know what they equal. There's going to be one thing missing. So F net is equal to the sum of all of our forces. F1 plus F air plus force of gravity. Okay, we know force net. We know force 1. Looking for force air. And we just solved force of gravity. So let's punch in some values and finish this thing off. Force net is equal to 0. Force 1 is 8.7 newtons. Force of air, we don't know, so we'll leave it as force of air. And the last one, force of gravity. It's acting downward. Downward is a negative value, so we're going to be adding a negative value or just subtracting. 3.4335 newtons. Okay. If we chug this all into a calculator, we end up getting force of air equal to negative 5.3 newtons. Or we can say this is F of air is equal to 5.3 newtons downward. Okay. That is our final answer. A couple things I just want to mention before I let you go is to watch out for this keyword constant velocity, meaning that our F net on the object is 0, and also making sure that you switch your units into kilograms, because grams are going to give you some wonky values. Okay, that's all.